us continue. Now this is a complete change of the setup, because instead of smooth curves and surfaces, we can see the polytopes. And so let me take vectors v1, so on vn in Rd, actually of the norm 1, and I will use them as the normals to the some polytop. And to define the polytop, take also h1, so on hn in R, and define the set P of VH as the set of all x in Rd such that Vi in a product with x is less or equal than Hi. So here V stands for the whole collection of VI's, H stands for the whole collection of HI's. So this set depends on V and H. VI is here, HI is there. So what is this set? This is a solution set of system of linear inequalities. Geometrically, this is the intersection of finitely many half spaces. So that's a convex polyhedron. And this will be bounded if, so under some condition on the VI's. If VI's look into opposite directions somehow, if they positively span the RD, then it will be bounded. So bounded if say in every upper hemisphere of ST minus 1, there is at least one VI. Minus 1 is always seen as the set of all points with norm equal 1. So this VI is actually lie in SD minus 1. And if in every open hemisphere there is some VI. Good, so in that case this is a convex polytope, and facets of this polytope have outward normals VI. Outward unit normals VI, but in fact, so every facet has a normal VI, but it can happen that for some VI there is no facet with this normal, because what can happen, so let us somehow draw the picture. So this what we have defined is this intersection of half spaces. But now if, and again, so HI is the distance here. If I take HI very big, then this line will run somewhere here, and my pentagon becomes a quadrilateral. So it will have less than n facets. So there can be less than n facets, in fact. That not all VI's define a facet. So let us consider only those collections of HI's for which it has n facets. So consider only those H. Well, so H is basically a vector in Rn, right? Because H is a collection of n numbers. Under those for which P of VH has n facets. So then these polytopes all have n facets, and these facets are pairwise parallel. So all such P of VH have n pairwise parallel. So pairwise parallel, I mean not between each other, but between two polytopes. So we have n facets with normals Vi. Okay, good. But still, so these polytopes, they are not necessarily combinatorially isomorphic. But they are not always combinatorially isomorphic. What does it mean to be combinatorially isomorphic? That means that if two corresponding facets in one polytope intersect, if they have a common edge or some other common smaller face, it doesn't imply that in the other polytope these two faces have a common edge. An example, one can take an octahedron. In the octahedron, in every four faces meet. Now, if you translate the planes of these facets in some way, then each vertex of degree 4 will split up in two vertices of degree 3. So this vertex of degree 4 can split in two different ways. It can be split like that, or it can split in the other way. So one gets different polytopes with the same directions of normals, but with different combinatorics. So this is the situation, and we want to consider only those polytopes which have the same phase directions and the same combinatorics. And they are called then strongly isomorphic. So let me put it as a definition. Two polytopes are strongly isomorphic if they have the same outward normals, so if their facets have the same normals, and the polytope combinatorially isomorphic. Well, a pedantic version of the definition should say that if one associates two faces, faces with the same directions of normals should be associated to each other, and this must be combinatorial isomorphism. But, are combinatorially isomorphic. So let us now take the family of combinatorially isomorphic polytopes. So let C subset of Rn. So this Rn is now our domain for the support numbers. Let C be such that all P of VH with H from this C are strongly combinatorially isomorphic. Strongly isomorphic. Strongly isomorphic. Good. So so C can stand for the word combinatorics. C is a choice of combinatorics for so for the given directions of normals. So now we can come to the mixed volumes in a different way. Namely, we will so I will state and give a hint how to prove the following theorem. If I consider all these strongly isomorphic polytopes, then the volume of this polytope is a polynomial in HIs. The volume of P of VH is a degree D homogeneous polynomial in H1, so on Hn, if so if H belongs to C. For H from this domain C. And I will denote this polynomial as V sub C of H. So let us look at an example. So what happens in dimension 2? In dimension 2 we have this picture. So let this be the origin. So let this be one of the HIs. So the corresponding direction is the vector VI. Then in this case the volume, so that is the area of this polygon, it is equal to 1/2 the sum of all HI times Li of H. So Li is just the length of the corresponding side, right? And this length, Li of H, is a linear function of H. In fact, it is a linear function of only these three lengths. So this is A times HI minus 1 plus B times HI plus C times HI plus 1. So this is not difficult to show. This is some trigonometry. So to compute this length from these three numbers. Note that, so what is given, the directions of the vectors are given. So what one knows are these angles. And if one knows these angles and these lengths, then one can compute this. This is some quite lengthy formula, but at least one can be sure that it is a linear formula. Good, and then one can see that this is a quadratic form, homogeneous polynomial of degree 2. In fact, so in all dimensions D, one can prove it by induction. And here one can say I have already done an induction step because, so the induction must be done a bit carefully. The next step would be to take three-dimensional polytope to write the similar formula. So the HIs times the areas of the faces, and the area of each face is by induction assumption a polynomial in some different variables, but these different variables depend linearly on H. And that's so the proof can be done by induction. All right, good. If we have this theorem, then we can define the mixed volumes for strongly isomorphic polytopes directly. Namely, if you have a so degree D homogeneous polynomial H, then it gives rise to a multilinear, symmetric multilinear form. Which I denote by the same letter VC, but now it takes D arguments, H1, so on, HD. So each of these HJs is a vector in Rn, right? So here I had a polynomial in n variables, because H was a vector in Rn. From a polynomial in n variables of degree D, I can make a symmetric multilinear form in the, yes, symmetric multilinear form on Rn. So somehow this multi is equal to D, D linear. And we just put by definition that the mixed volume of polytopes from our domain, so of these polytopes with the same combinatorics, the mixed volume of strongly isomorphic polytopes I define it as a volume of P of VH upper index 1, so on P of VH upper index D. This is exactly our symmetric multilinear form evaluated at H1, so on HD. So that's in fact an alternative way to define the mixed volumes. One does it for so for this class of polytopes, but then in fact any collection of convex bodies can be approximated by strongly isomorphic polytopes. And then one can define the mixed volume by continuity. Okay, so this is of course some preparation, and so what do we prepare for? Let me give also another example. Again in dimension 2. The mixed volume of two polygons. In fact, polygons is a very nice case because all of them are strongly isomorphic. No change combinatorics can happen. So if you have directions of sides, then no matter how you move them, you should only take care that one side does not disappear somewhere, but they are all strongly isomorphic. So then the mixed area of P of VH. So what notation should I take? So it's built, yes, it's H1 as before, H2. This is 1/2. So the sum I from 1 to n. We have an n gone H1I times L. So we had this function L in the formula for the area of a polygon. So we take exactly the same linear function L and apply it to H2. This is not obvious that this formula is true because it is not obvious that this expression is symmetric in H1 and H2. It is symmetric because it is Hi2 L of H1. So this equation, this equality, it's in fact we had something similar to the formula for the mixed volume of K, L, so on L, which we had at some point. So that is something that must be proved here, but if one proves it, then the formula for the mixed area is like that. Good, so now let us look again at the Alexander-Fenhill inequality. So 6.2. Alexander-Fenhill inequality. We visited. This inequality is not very well known because it has quite a complicated formulation, and mixed volumes is something that not everybody knows. But I want to show that this inequality actually should be formulated in a different way, and then in that way it becomes something very attractive and easy to remember. Good. What was, by the way, the Alexander-Fenhill inequality? It was the following. If you take the mixed volume, nobody knows what it is. I mean, you already know, but usually not many people do. MD minus 2 squared is bigger or equal than the volume of KK, then the same M's times the volume of L in the same M's. So I want to show that this is equivalent to the statement about signature of a certain quadratic form. To define this quadratic form, let us fix some h1, so on hd minus 2 in our domain C, which defines strongly isomorphic polytopes. And put q of x, y to be, so the corresponding polynomial C. So with every C, one can associate this polynomial as I did. This is a multilinear form now, right? In this multilinear form, we substitute x, y, and the fixed vectors h1, so on hd minus 2. So this is a symmetric bilinear form. And every symmetric bilinear form has a signature. N plus, N minus, N0. So this is the number of coefficients, positive coefficients, negative coefficients, and zero coefficients if you diagonalize this form. And this is independent on the way how did you diagonalize, right? So that's the signature. And what do we know about the signature of this? What do we know about the signature of this Q? Well, so it should be also maybe mentioned that we know that there is at least one positive direction because Q of H is equal to the mixed volume of P of HV, P of HV, then P of H1V, well, P of HD minus 2V. And this is a mixed volume of convex bodies. It is always non-negative. Well, it's even positive if these are really convex bodies, if they have non-empty interior. We did not prove it, but that's a useful fact about mixed volumes. So if you take bodies with non-empty interior, then this is positive. All right, so that means that n plus is at least 1. Because for diagonalization, we can use this vector as the first basis vector. I state now the theorem that n plus is exactly equal to 1. And this theorem is in fact difficult because it's exactly as difficult as the Alexander-Fenhiel inequality. I will show that it is in fact the same. So claim this fact n plus equal 1 is equivalent to the Alexander-Fenhiel inequality. Okay, I said that this formulation is somehow more attractive, but again, it deals with some quadratic form that comes from some complicated construction. I want to motivate this a little bit more before I prove this claim. Because this function, so if you take h1 equal hd minus 2, this quadratic form q is in fact the second derivative of the volume. So let me denote it by g. Q of xy is in fact the second partial derivative of the volume of p of g v. Well, I think I have muted now the arguments, it doesn't matter, so p of g v, the partial derivative in directions x and y. So now x and y are not real variables, x and y are both vectors, so I'm taking direction derivative in one direction and then direction derivative in the other direction. So I state it again without proof, but the proof follows from the multilinearity of mixed volumes. And so it motivates the study of this form additionally, right? So it says that the second derivative of the volume has certain signature. So it has one positive direction and not more. In fact, this was used by Bavard and Dries. I forgot the title of the paper, but it was about shapes of polygons. Because this signature is, of course, so everybody who does hyperbolic geometry, they like this signature. What we have is one positive direction, and then everything else is negative or 0. That's exactly the signature of the Minkowski in a product, so in the Lorentzian space. And if you have this quadratic form, then it allows you to define, so it gives you a hyperbolic plane. So what Bavard and Dries, Bavard with D, what they did, they took this quadratic form for d equal 2, and they studied the space of polygons with fixed directions of areas and with fixed directions of normals. For every chosen set of normals, this gives some hyperbolic polyhedron. So somehow the space of polygons becomes itself a polyhedron of some higher dimension. So that's a very nice construction, and so I also invite you to read this paper. In fact, they also prove this signature, the fact about the signature of this quadratic form in a different way. In the case of dimension 2, there are different ways, different easy ways to, different ways to prove this fact. This fact. Then also jointly with François Pilastre, we have looked at the shapes of polyhedra. So where we already have taken d bigger than 2. And then again, so this quadratic form, it has some more or less geometric meaning. It can be, if d is equals 3, it can be taken to be the area, the surface area of a polytope. And again, this gives some hyperbolic space, and the space of strongly isomorphic polyhedra defines some hyperbolic polyhedron in that space. In fact, also in this article with Pilastre, one can find more about the combinatorics of the polytopes and these strongly isomorphic polytopes. And so how can one deal with them? All right. That was just to make the point that this quadratic form is not something completely exotic. It has a geometric meaning. Now, why this inequality is equivalent to the statement about the positive index. Let us write the Alexander-Fenhiel inequality in the new notation. Alexander-Fenhiel is, in fact, in these notations, means that Q of, so in place of xy, one should take not just any vectors, but the support vectors of polytopes. So Q of hg squared is bigger or equal than Q of hh times Q of gg. This is just rewriting the inequality in our new notation. So proof of the claim. Good. Let us go in this direction. Assume we know that n plus is equal 1. What is actually n plus? N plus is the maximum dimension of a subspace on which the quadratic form is positive definite. So is maximum dimension, how do we denote the subspace? Usually by V, dimension of, maximum dimension of A, dimension of A such that A is a subset of Rn, and Q restricted to A is positive definite. So if n plus is equal 1, then there are no two-dimensional subspaces in which the form is positive definite. In particular, Q restricted to the linear span of G and H. Now G and H, so they are here, is not positive definite. And this implies that together with the fact that Q of HH is bigger than 0, right? Q of HH is a mixed volume and it is bigger than 0. This implies that the gram matrix of Q in the basis QH, in the basis GH, has negative determinant. Determinant of Q of HH, Q of HG, Q of HG, Q of GG. This determinant is less or equal 0, right? Yes, so we have a two-dimensional space, a quadratic form on a two-dimensional space, which has at least one positive vector, but it's not positive definite on the space. If this determinant would be positive, then it would mean that actually that the form is positive definite. But the form is not positive definite, therefore the determinant is less or equal 0. But that's exactly the Alexander-Fenhiel inequality as is written here. So this was one direction. The n plus equal 1 implies Alexander-Fenhiel inequalities. In fact, the arguments can be reversed, and they prove also the reverse, the converse implication. Good. So in the remaining 20, yes? Yes, exactly. it exactly does. So the equality case, the dimension of the kernel, let me put it as a remark. Thank you for asking. I was not going to say that, but thanks to you, so n0, which is the dimension of the kernel of Q. Well, kernel is not a very good word if one speaks about the symmetric bilinear forms, but it has some basis. Yes, and this is related to the equality cases in the Alexander-Franklin inequality. In fact, for the polytopes, I think, actually I'm not sure, so I don't know exactly in which cases the equality cases are not known. Maybe for polytopes they are known, but one cannot use approximation to find the equality cases. Even if you know the equality case for polytopes and you approximate something, then a strict inequality can become an equality in the limit. But somehow the dimension of the kernel is at least D. This is because you can translate the polytope in D directions, and all translations of the polytope, they give you an element in the kernel. And also this n0 is equal to D, it is somehow related to rigidity questions. Rigidity questions. Maybe I will speak about one of these if I will have time. Because now that is another goal, namely to speak about the discrete spherical Laplacian. Discrete spherical Laplacian. So this is, in fact, something new. Discrete Laplacians are very well-known objects. If you have a function f on some graph, in fact, on the vertex set of some graph, but let us say this is just a function on Rn, then the discrete Laplacian of f is given by the sum of aij fi minus fj, whereby fi I denote the, what did I denote by fi? No, actually f must be not on Rn, excuse me. So f is defined on some discrete set, on some finite set, 1 n to r. So discrete function is function defined on just a finite set of points, and fi is f of I. So then something like that is called discrete Laplacian if just called like that if aij are bigger or equal 0. But the choice of these coefficients of the Laplacian, this is a delicate matter. There are combinatorial Laplacians where the coefficients are just equal to 1 and one considers a graph. That's already a big theory. But if your graph comes from some geometric situation, like graph of a polytope, then these coefficients must carry some geometric information, of course. So to motivate what will follow in discrete case, let us again look at the formula formula that we had in the smooth case. So the second Quadrant integral was 1 over d integral over the sphere h times h minus the Laplacian of h divided by d minus 1 integrated with respect to the volume element on the sphere. In the polyhedral case, there is a formula. If P is a polytope, then this is equal to the sum I from 1 to n hi times the mixed volume of fi of h, and then d minus 1 copies of the vector 1. I mean, so here I have to skip some details, but 1 is just a vector of, so this end is 1 in Rn, and we are looking here, of course, at the strongly isomorphic polytopes, and in fact, these are polytopes with the same combinatorics as the polytope with hi is equal to 1. So the polytope with this, with hi equal to 1, is a circumscribed polytope. Right, because hi gives always the distance from the origin to the plane. So we have planes at distance 1. This is a circumscribed polytope. And this is sort of discrete sphere. But this discrete sphere, it depends on the choice of the vectors vi, of the points on the sphere. So what is here is sort of mixed mixed d minus 1 dimensional volume of d minus 1 copies of the sphere, so of the ball, and 1 copy of the polytope P. Good, but then just by analogy, well, as Steiner did, he did it also first by analogy. If you look at these two formulas, then we can define this to be like a discrete inner product of h and certain function of h. So get a discrete version or discrete analog of the L2 product of h and h minus Laplacian h divided by d minus 1. So from this formula, one can, by definition, somehow say that. I mean, so the best what one could do is to say what are the coefficients here and to define the spherical Laplacian like that. What is directly possible is to define the Laplacian in sort of weak sense as so by saying how it acts. So what is its L2 product with any other function? Then if one, the problem is that in this discrete case it's not completely clear how to define the inner product. So there are some better ways, worse ways, but it can depend what is better. Anyway, so we get this analog, and one can prove a statement about the spectral gap of this discrete Laplacian. Because the inequality that we have proved in the first hour today, so the inequality W2 squared, or W1 squared, sorry, now it will be W1 of P, of the polytope P, bigger or equal W0 of P times W2 of P. We have proved it from the fact about the spectral gap of Laplacian in the smooth case. But the inequality is true anyway, so one can prove it one can prove it also by some different method. And this inequality implies now in the opposite direction that the spectral gap of this operator is d minus 1. Lambda 1 is equal to d minus 1 for the plus h defined above. So not exactly actually what one proves is that this this quadratic form is is non-negative definite. That this is equivalent to that spectral gap. So this one gets basically for free. Just that is a very efficient way of proving theorems. It's just by setting right definitions. So in this way, I have proved the theorem because I have defined something in such a way that the theorem becomes obvious. But this, in fact, motivates that the definition is a good one, because what is defined is a new object. All right, but one can then go further and look at the spectral gaps not on the sphere, but on some other Riemannian manifolds, and that is the Lichner-Rovitz theorem. If M is a manifold with Ricci curvature bigger or equal to d-1, let M be a d-1 dimensional Riemannian manifold closed without boundary. Well, without boundary. Well, closed. So compacted without boundary. Such that the Ricci curvature is bigger or equal to d-1. One times the metric tensor. Then the smallest non-zero eigenvalue lambda 1 is bigger or equal than d-1. Yes, I haven't put Lichner-Rovitz. So the sphere has Ricci curvature exactly equal to d-1, and for the sphere, the first non-zero eigenvalue is equal to d-1. The theorem says that if the curvature is bigger than the curvature of the sphere everywhere, then the spectral gap is bigger. That is also an addition by Obata, which hence the equality case. If lambda 1 is equal to d-1, then actually it must be a sphere. Good. One can now try to extend this theorem to the discrete case and try to prove sort of discrete Lichner-Rovitz theorem. But for this one needs to define discrete analogs of metrics with curvature bigger or equal to d-1. So this is, in this case, these would be spherical cone metrics. So what is a spherical cone metric? The easiest way to see it is to take a set of spherical polytopes and glue these spherical polytopes together along the faces. When you glue the spherical polytopes together along the faces, if you have had a very good set of polytopes, then you can glue from them the round sphere. But maybe your polytopes, when you glue them together, so here was the angle of one polygon, if I'm in dimension 2. Maybe when you glue them together, then the total angle here, maybe it is not equal to 2 pi. So you cannot do it in the space, but you can do it abstractly. So you get a metric space with singularities. So this point is a cone singularity. In higher dimensions, these cone singularities, they occur along a codimension 2 subset. So if we assume that all these angles are smaller than 2 pi, then this can be viewed as an analog of curvature bigger than 1. So this is a discrete analog of Ricci curvature bigger or equal d-1. Yes. Because in these polytopes, itself, the curvature is exactly 1, and here there is some even more positive curvature. And so a question, problem, is there a discrete Lichtenloyd theorem and I can prove it in dimensions, well, d equal 1 is something simple, but in dimension 2 it also works. So in dimension 2, yes. I mean, again, so this discrete Lichtenloyd theorem must be stated for some Laplace operator, and one can define this discrete Laplace operator in the somehow in the same way that I did for the sphere. So that's of course the high dimensions is a question, and that's I find this is an interesting question. All right, so then I will finish here. If you have any questions, just ask now or later. I'm here till tomorrow morning.